Welcome back to Old School Math. Today I'm going to be showing you an overview over function families. By the end of this video, you will be able to identify function families by their graph. Also, you'll be able to identify key elements of different functions. The first function that we're going to talk about today is the constant function. And I just chose y equals 2 because, well, that's a pretty easy number. Really, y could be anything for a constant function. If you look at the table, you see here that all of the values are 2 for y. That's why we call it a constant function. You see on the graph, every point has a y value of 2. So it has a slope of 0. Also, we could call this a straight line. So when we're looking at function families, we want to identify the shape, kind of what's going on with the slope, how the function's changing, and we're also going to talk about domain and range. Now the domain is all of your x values, and that is all the x values that work for this function. There's no reason that we couldn't have x values that are less than -10, -100, -1000. They could keep going on forever in the negative direction. So we would say the domain would be from -infinity all the way out to +infinity. That is, there's no x values for this function that don't work. The range are going to be the y values for our function. And the y values would just be whatever our constant is. For this case, our constant is 2, so that's what our range is. That's the only y value that is ever going to show up on this graph. So I'm going to write constant here. And I'm going to put it in parentheses so that we know whatever that constant is, that's what our range is going to be. If our constant was y equals 4, then the range would be 4. That's the only y value that would work. We're going to talk about domain and range for a lot of these different functions, and so hopefully by the end of it you'll start to think, okay, this is what the domain would be, and this is what our range would be. The second function that I want to talk with you about is the linear function. That is in the form y equals x. Now we could have a coefficient in front of x, we could add or subtract x by something here, but we're always going to have a y equals some kind of x. For just this basic function, you see what the table looks like. In the table, every y value is equal to whatever x coordinate that I'm looking for. This is what our line looks like. Some key features, we might say that it is a straight line. It has a slope. So the word linear actually means line. That's where it comes from. Let's talk about the domain and range for this thing. We could put in any x value. When we see this tail come in this direction, we see it going down, but we also see it moving to the left. So our domain would be all the numbers from -infinity. And then over here, we see it also going to the right forever. So it would be from -infinity to +infinity. Now the domain on this one, we could tell that it's going to be -infinity to +infinity because there's no value for x that I can't include, right? I can put anything in for x. On the range, we see the same thing happening. We see all the numbers from -infinity to +infinity as possibilities on this graph, right? This is going to keep going down forever. That's going to keep going up forever. So the domain and the range are just both -infinity to +infinity. A little bit different from our constant function. The third function that we're going to look at is the absolute value function. Y equals absolute value of x. These bars beside x mean to take the absolute value, and that just means how far is this number actually removed from 0. So what this does to our negative x values is it turns them into positives. So -3 corresponds with 3, -2 corresponds with 2, and so on. It doesn't change the positive x values, however. we see on the graph it makes a V shape. So anytime we see a V-shaped graph, we should automatically know it's going to live in the function family of absolute value. The domain is going to be all real numbers or negative infinity to positive infinity. There's no x value that wouldn't work for this thing. They keep going, the graph keeps going out in both directions. So the domain is negative infinity to infinity. And the range is a little bit different here. The range on this thing starts at 0. We see the lowest our y value can actually go is 0. Now we're going to put a bracket instead of a parenthesis around 0 because the bracket means that you can actually include that value. We can't ever really get to infinity, so that's why we put parentheses around the infinity signs, but the bracket means we can actually touch 0 on this graph. And then we touch 0 with this function where x is 0, y is 0. Now the range extends in both directions up to infinity. So the range would be from 0 included all the way up to infinity. Let's talk about two other things on this graph. It does have a minimum value. And the minimum value is just the lowest place that the graph would go. We see here the y value for our minimum is 0. Another thing that we could talk about on this graph that we haven't talked about on the other graphs is that it's symmetrical. We see the left side of the graph is the exact same as the right side of the graph. So we would say it has y-axis symmetry. That is, if we folded the y-axis over, we would get a reflection there. So it has y-axis symmetry. The next function is the quadratic function, y equals x squared. We see on the table every x value gets squared to get our y value. Negative 3 squared is positive 9. If you put this in your calculator, you might be tempted to punch in negative 3 squared, but that's going to give you negative 9. Your calculator doesn't know that you're trying to put the whole negative 3 and multiply it by another negative 3. If you do that in the calculator, make sure to put the negative in parentheses with the 3 and then square the whole thing. We see these decreasing to 0 and then increasing back up to 9, and they would keep increasing greatly from there. We typically call this a parabola. And it is a U shape. Let's talk about the domain and range. The domain, there's no value that won't work for x when we put it in here. We can put huge numbers in for x. We can put super big negative numbers in for x, and we will always get a y value out from that. So the domain is negative infinity to positive infinity, or all real numbers. And then the range looks like this. The lowest our y value can go here for this function would be at 0. So since we can actually touch 0, we'll put a bracket. And we see that the left and the right side of this graph both go up forever. So we would say that's from 0 to infinity. Okay? Now, like the absolute value, this also has a minimum. And similar to the absolute value, it is symmetric. Forgive my shaky hand as I was drawing this graph. But we see that it has symmetry along the y-axis here. If we folded the left side over, we would get a mirror image. So we would also say it has y-axis symmetry. The third function that we're going to look at is the cubic function. Now the cubic function grows super quick compared to the quadratic. You see that this third point I had to put way up here. I don't know where it is because my graph only goes up to 10. But we should see that at 3 times 3 times 3 gives us 27. Some funny stuff happens when you start cubing fractions, but we know that number is going to be really small there. So on my graph, we see an extremely steep growth. I would kind of call this an S-shaped curve. And anytime you have something that is x cubed, it's going to have some type of S-shaped curve to it. Let's talk about the domain and range on the cubic function. So the domain, again, there's no value that I can't put in for x here. So the domain is negative infinity to positive infinity. And the range is the same. We see super negative y values and super positive y values. They would continue on forever. Now, if we talk about the symmetry in this graph, the symmetry might not be obvious. But if you remember from geometry, you learned about rotational symmetry. If we took this graph right here on the origin and rotated it around, we would get a reflection on itself, or we would get a rotation onto itself. We call that symmetry about the origin. So if you put a point down on the origin and you rotated this graph 180 degrees, it would land on itself. So we would say it has symmetry about the origin. The exponential curve is a lot different than the other ones we've looked at so far. And honestly, a lot of people see this curve here and they automatically call it exponential growth, but sometimes we could have growth that would be quadratic or cubic or quartic and be pretty similar. But one difference in this graph is that every time you increase from the x value by 1, the y value doubles. We double from 1 to 2 to 4 to 8. And then as we work backwards here, we see the y value getting cut in half. And that's because of 2 here as our growth factor. Key features on this thing, it grows rapidly. Another thing to note for the exponential curve is there is no symmetry. And if we talk about the domain and range, there's no limit to the x value. So the domain would be all real numbers or negative infinity to infinity. But the range gets interesting. Now we don't have any values here that are actually 0. But if we kept taking half of these numbers on and on and on, we would get values that get super, super close to 0. So since they never actually touch the x-axis, we actually don't have a exact minimum value, but we do know that the lowest value that we could, in theory, get would be 0. Since we actually can't get to 0, but we can get super close to it, we would put a parenthesis around 0. It does, however, start to spike up on the right side of this graph, and so it grows to infinity. So the range would be the numbers from 0 to infinity, but not including 0. Another thing to note about this exponential function, since it's not going to cross 0, the y values won't ever be negative. Now, all this can change if we start doing transformations, but for our typical function, just we won't have negative y values. The rational function is a bizarre function. It's y equals 1 over x, or you could have some variation of that. But in our just standard rational function, you'll see that there are kind of two pieces to this graph. One on the left side which has negative values, and one on the right side that has positive values. Both have a curve and both get really close to the x and y axes. We call these asymptotes. And an asymptote is just a place on a graph where the line will get really close to, but it won't actually touch it. Okay? Now, some key features here on this graph would be that it is in a couple pieces. It's broken apart. Okay? Another key feature of this thing is that we get an error at 0. We can't ever divide a number by 0, so that's why we get that error there. When we put in 0 for our x value, we can't get a y value. So we would say there's no x value there, or we would have an asymptote on the y-axis. Okay? Let's talk about the domain and range on this thing. So the domain, this looks like it's coming out here to negative infinity, and the domain on the right side looks like it's going to positive infinity, but we know in the middle we can't have 0. So here's where we're going to use interval notation, and it gets kind of interesting. Negative infinity, we said we can't have 0, so we're going to put a parentheses around it, but we also have another piece to it. And so we use what's called the union, which looks like a capital U without the little tail. And we're going to pick back up at 0, and we're going to go to infinity. So all this means is that we have a break in the graph where the x value is 0. We can be all the numbers up to 0, all the numbers past 0, but it just can't be 0 itself. The range is very similar. The range is all the values from negative infinity to 0, but we never actually touch 0 here. We have another asymptote. And then we have the values from 0 on up to infinity. So here we've got the square root function, y equals square root of x. And when we're looking at this graph, we see that it's kind of got a, kind of like a half hill shape to it, if you will. But it only lives on the right side of the graph. It doesn't come over here into our negative x values. If you try and take the square root of a negative number, you'll get an imaginary number. We'll talk about that later, but your calculator will probably just tell you that there's an error. You can't take the square root of a negative number. So, if we look at this, the domain would be any value from 0 to infinity, since those are the values that we can actually put into our graph. Now keep in mind, I'll put a bracket right here around 0 because we can actually get a y value from that. We can actually get that the y value is 0. The range looks pretty similar. It's also from 0 to infinity, including 0. The lowest y value we can get on this graph is 0. Okay? As we work through this table, we stopped at 3, and the square root of 3 is, or when we put in 3, we get square root of 3 for y. It's about 1.7. If we put 4 in here, we would get 2. So let's make sure that on 4, 2, we've got a dot, and the line is going through that. So 0, 0, 1, 1, 4, 2 would be the points that we would want to look at when we're making this curve. Okay? There is no symmetry on this thing, and the square root is just kind of a funny function. The thing to keep in mind is that you can't have negatives in a square root, so they shouldn't live on your graph. So I've drawn my cube root function, and if you see, I extended my table up to -8 for the x value and +8 for the x value to just find a couple more points that actually, made some sense to graph on here, right? The 1/2 and the, cube root of 2 are hard to actually put on here, But so these values are actually useful here, okay? Now, this looks pretty similar to the x cubed function, but we know that it has been kind of shifted around and flipped. But it does have origin symmetry. It has a similar S shape as our cube root function, or as our cubic function. And another thing to note is that the domain is all real numbers, or the numbers from negative infinity to infinity, and the range, again, is all the numbers from negative infinity to infinity. Now you're saying, how does this go into infinity on the y-axis? Our x values will have to be absolutely massive to get this to go up very high. But they do keep increasing, right? Just slowly. Unlike the square root, there's nothing that we can put in this that makes it not work. We can take the cube root of a negative number, and if you don't believe me, try taking the cube root of -8 in your calculator. You'll get -2. Well, I know that was a lot to take in all at once for all the different function families that we're about to look at in this unit, but I appreciate your time in it. And if you have questions, hang on to them, because honestly, we're probably going to cover a lot of this in more depth as we continue through the unit. Thanks for watching this video, and please subscribe.